Thanks again for the great talk. And next, it's my great pleasure to introduce our third keynote speaker, Professor Chelsea Finn. Chelsea is an assistant professor in computer science and electrical engineering at Stanford University, and also a co-founder of Physical Intelligence. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. To this end, her work has pioneered end-to-end deep learning methods for vision-based robotic manipulation, meta-learning algorithms for few-shot learning, and approaches for scaling robot learning to broad data sets. Her research has been recognized by awards such as the Sloan Fellowship, the IEEE RAS Early Academic Career Award, and the ACM Doctoral Dissertation Award, and has been covered by various media outlets. She received her bachelor's degree in electrical engineering and computer science at MIT, and her PhD in computer science at UC Berkeley. Let's welcome Chelsea for the talk.
Thank you for the introduction. So I'm really interested in how we might develop foundation models for robotics. I don't need audio. Okay. Great. And as part of that, I think we could potentially take some inspiration from how we've seen foundation models in other domains, like in language models. And typically in language models, we look at a training paradigm where we first pre-train on very large amounts of low-quality data, followed by a post-training phase that has a supervised phase and a reinforcement learning phase. And I think that if we look outside of the domain of natural language, it's actually a little bit tricky to think about how we might develop such a foundation model and how we might develop a paradigm for this. And in domains such as robotics, for example, we don't have an open internet of robot data, so we can't necessarily follow exactly this low-quality pre-training and high-quality post-training formulation. And there's also other challenges, like having to do high-frequency control of continuous actions. So what I'd like to talk about today is a little bit of a story of how we developed a foundation model for robotic control at Physical Intelligence. This is kind of the start of, I think, a journey of developing more flexible and more broadly capable foundation models for controlling robots. And this model we pre-trained on 10,000 hours of data. Now, by machine learning standards, 10,000 hours is not all that huge, but by robotic standards is actually by far the largest data set of robotic manipulation data. And it was actually a very fun journey to start to see what this is capable of. And specifically what I'd like to talk about is a bit of a story on how we post-trained the Pi0 model to do complex tasks. And as an example of this, in this video, here the robot is using a single neural network model to unload a dryer into a basket, bring that basket over to the table, and fold all 5 items of clothing items that are in the basket, all fully autonomously in a single uncut video. And it does all of this in about 10 minutes. I'm going to talk about this in part because I personally worked on this quite a bit with Michael and Suraj, and of course with the support of the whole Physical Intelligence team. Cool, so we'll watch it do a couple more items. I should mention that this sort of task is actually, it's very easy for people to do, but it's incredibly challenging for robots to do because you have to handle the variability of the ways in which shirts can be crumpled, the way in which they can, you can kind of actually encounter them after being dried in a dryer. Okay, so how do you even start to approach developing a neural network that could do something like this? So we started doing this started getting set up in March of this year. And we started with fairly simple tasks, like can we fold a single size, single branded shirt when it starts flat on the table? Or can we flatten one shirt? And to do this, we applied standard imitation learning, where we collected data, demonstration data through teleoperation, and then we trained a neural network policy that had around 100 million parameters to output the joints at 50 hertz. So you did this with kind of standard imitation learning, supervised learning. And in May, we were able to get a policy that could fold a shirt like this. And it's able to do this repeatedly. It has actually a pretty high success rate. It's also able to do it with shirts of different colors. But they're also all roughly the same size shirt, and they all start flat on the table. We also did an experiment where we trained a policy to flatten a shirt. So maybe it starts crumpled, and then it waves it in the air in order to flatten it. So these are pretty simple tasks, and they're fairly simple to train a neural network to do. So we did that in May. And after that, we wanted to see if we could then start to make it incrementally harder towards the full laundry scenario that I mentioned. And so, in particular, instead of starting the shirt flat on the table, we started the shirt crumpled in arbitrary configurations. And it turns out that this doesn't make it just a little bit harder. This actually makes it a lot harder. And so here's some examples of what a policy trained on data to flatten and fold this shirt looks like. And the robot ends up fairly aimlessly trying to manipulate the shirt in different ways without actually successfully flattening it and folding it. And we tried a lot of different things, and we ran a lot of different evaluations. So here's the success rate of many of the different things that we tried, so all 0% success rate. It's really, really hard to get the neural network model to do something like this. Had a lot of failures. This was over multiple months. We started to see a little bit of signs of life after about a month or two. Again, with the kind of the same imitation learning strategy, here's one successful rollout where it's able to flatten the shirt and it starts folding it here. It's not necessarily the cleanest fold in this example, but it's able to, I would say, be able to successfully fold the shirt on the table, starting from a crumpled seam. But it still didn't work that well. It's still quite inconsistent. We transitioned to moving towards a laundry basket because this doesn't really make the task harder because it just needs to take it out of the basket before flattening it and folding it. But again, we're seeing lots and lots of failures. We tried adding history to the policies. We tried training the policies for longer. We tried using end effector control instead of joint control. Or we thought maybe the calibration of the encoders in the robot was a challenge, or conditioning it on different factors, hierarchy, higher resolution images, intervention data. We considered a lot of different things. And the thing that actually seemed to really move the needle and actually start to get this to work after 2 to 3 months of failure was starting to move towards a paradigm of pre-training and then post-training, where instead of training on all of the data of folding the shirts, we took 1,000 demonstrations that were the most consistent and the most high quality, and we pre-trained on all the folding data and then fine-tuned on this more narrow set of data. And we found that when we did this, we were able to get a policy that was actually a lot more successful than all of the failures that we had seen before. And in particular, this is one of the videos of one of the first times it folded 5 items in a row in September, so multiple months later. This is actually one of the most exciting moments I personally had. It felt like it actually really worked when I was able to fold 5 items in a row. Now, there's still a long ways to go because it takes about 20 minutes to fold 5 items. And as you can see, it actually messes up. I think on this blue shirt, it might have actually tried folding it and then making a mistake at the very end and then retrying 7 different times before it actually eventually was able to fold it. So very far from perfect. But it's actually able to accomplish the task eventually. And then lastly, sometimes the fold quality varies and the success rate isn't always 100% and so forth. So I think this might be the last attempt. Yeah, so here it finally folded the blue shirt before moving on to the orange shirt, and then eventually is able to fold all 5 items and stack them on the table. Another example failure that it had to make is it would fold it and then stack it and then push the stack towards the corner and then push it off the table, which was a little bit of a very sad failure mode when that happened. We then, once we actually realized that this sort of post-training strategy was very helpful, we then curated the data set to include an even higher quality set of demonstrations with higher rated folds. This was maybe half a month later, and we found that this indeed kind of improved the performance of the policy, and it went from doing 5 items in a row in 20 minutes to 5 items in a row in 12 minutes. And so this is also quite an improvement, and was quite exciting to see the robot be able to do this very challenging task. Now, here the fold quality still varies, and 12 minutes is still shorter or longer than it could be. And so, actually, maybe before I move on to our next step, so far I've just been showing qualitative results. Now, what if we look at quantitatively? Does post-training actually help compared to just training on everything? And so, what I'll be showing here is that y-axis is going to be showing task progress. So, you make around a quarter of progress if you take it out of the bin, then a little bit more progress if you flatten it, more progress if you fold it, and then more progress if you stack it. And in terms of average task progress, we found that if you use post-training, you have significantly higher average task progress compared to just training on all of the folding data. And this gap looks actually pretty large, and it's actually even larger than you think, because really the policy that's trained on everything is really only able to get it out of the bin and really struggles to flatten and fold and stack. So to post-training on the highly curated data leads to substantial performance improvements. Now at this point, everything I had shown so far, all the videos were a neural network with around 100 million parameters. There's a transformer neural network. And this is where we started to use pre-trained vision language models. And specifically, independent of the people working on post-training, such as myself, the folks working on pre-training got their act together and gave us a nice pre-trained model. In particular, this pre-trained model used the PolyGemma vision language model, which is an open source vision language model that uses the Gemma language model and the SIGLIP vision encoder. We then took this pre-trained vision language model, which has 3 billion parameters, and passes input robot images from the robot's cameras, passes input a language command describing the task that the robot should do, and also incorporate an action expert that's attending to all the internal values of the language model from this VLM. This action expert gets the join angles as input and predicts a sequence of actions, a sequence of target join angles in order to solve the task. We're using a flow matching objective, which is you can think of as a version of diffusion, which we find to be especially effective for predicting complex distributions of continuous variables, which these join actions are. So for example, for the robot that we saw before, it has 6 different joints on the arms as well as the gripper, and so you get around 14 different continuous values that you're predicting, and you predict 50 of them, one for each time step into the future, to predict 1 second of future actions. So we took this model, this pre-trained vision language action model, instead of just being pre-trained on all the folding data, it's pre-trained on all of the robot data that we had collected, in addition to other open source robot data. And beyond that, we just took the same exact post-training data set and applied it to this new model that was pre-trained on all the robot data. And we found that actually the new model significantly improved performance. So instead of being able to do 5 items in around 12 minutes, it's able to do 5 items in 9 minutes on the left, and also be able to, like, there's kind of more videos of doing 4 items in 5 minutes and 4 items in 7 minutes. So it's faster, leads to higher fold quality, and is also just more consistent in terms of its performance. So it's pretty cool that we're able to kind of independently develop a pre-trained model and a post-trained data curation. A few highlights of what this model is able to do. So these are shorts that the model has never seen before. And this scenario where it's folded under is actually really challenging. And the policy is able to figure out that it should reach under the shorts that are folded under to grab the part that's underneath in order to flatten it before it starts to fold it. So this is a kind of behavior that is kind of pretty cool to see and pretty sophisticated from the model. After it flattens it, then it starts folding it. We also find that sometimes if it doesn't have the corners of the shirt, it will, instead of then continuing to try to wave the shirt to flatten it, it will then kind of expose the corners by folding the shirt over and then wave it in the air to flatten it again and then start folding it. And then it's also able to handle unseen clothes. So I mentioned some unseen shorts before. Here's a shirt that is a V-neck, and it didn't see any V-necks in the post-training data set and had never seen this shirt in pre-training or post-training. It still makes some mistakes where it will excessively kind of wave it in the air if it's not sure how to do it, but it is able to fairly efficiently flatten the shirt and fold it, even though it's never seen this particular shirt before. And then after the shirt, there's a shirt with buttons on it, and it also didn't see any shirts with buttons on it in the training data, and it's able to also generalize to this shirt as well. And so, again, a really complicated task that it's also able to do with completely novel objects. So watching robots fold shirts might not be the most exciting thing to do. Whoops. So we can speed it up a little bit. but it is able to fold the shirt quite nicely with the buttons on it. And then it's also able to handle interruptions. So this is kind of showing how reactive and how it's able to handle these different unseen situations. So here we interrupted it by putting a shirt on the table, and it's able to kind of put it back and then focus on the shirt that it's trying to fold. We can also undo some of its folding progress. So here, again, Michael is going to come in and unfold part of the shirt, and it'll kind of lay it flat again and fold it. Michael will then unfold the other part. It'll then try to find the corner and then fold it again. And it's able to react and eventually get to a folded shirt. Cool. So those are all qualitative examples of what this policy is able to do. And I mentioned this kind of pre-training and post-training being very helpful. Quantitatively, if we look at pre-training and post-training and compare it to no pre-training and compare it to no post-training, we see, again, a really substantial improvement in the progress that the policy is able to make and ultimately the overall success rate. And so this bar is showing if you don't use any pre-training, you train directly on the curated data set, it really struggles, suggesting that it's able to leverage the pre-training to know what to do in a variety of different scenarios, not just the scenarios seen in the post-training data set. And the post-training really helps it figure out what strategy to follow in order to do the task well. Now this was all in laundry, and all the videos I showed were on a static robot. We can also translate this recipe to the mobile robot, which is the first video that I showed. And we took the same recipe where we took a high-quality folding data set. We also incorporated two other parts of this task, which are unloading and transferring the laundry to the table. And it's able to, we're then able to kind of add all this data set to a single post-training data set to train a single policy in order to do this task. Now, does this work beyond laundry? We also collected data for some other complicated tasks and tested whether or not we could curate data sets and train the robot to do this. In this video, the robot has to construct the bottom part of a cardboard box, which is very challenging because you have to fairly delicately configure the box into a configuration that will allow you to fold it. And there's many ways in which the box can get unfolded or unconstructed. It can also do tasks like putting food into a to-go box and putting eggs into a carton of eggs and closing the carton. And quantitatively, these are actually tasks that are not in the pre-training data set. And we find that this sort of pre-training and post-training paradigm also works well in that scenario. And we see that if you, the pre-training is less helpful as before. So in some cases, if you just train from scratch, it does okay, especially on the packing egg task, which is a little bit easier because it's just picking and placing. But for to-go box and building a box, we find that the pre-training is helpful, even though these tasks are not in the pre-training data set. And lastly, if you just try to apply the model out of the box, because these tasks aren't in the data set, it's not able to do so without any sort of post-training. Cool. And then the last thing that I'd like to mention is that when we have robotics models that are actually starting to work well, it means that you can apply those models not just to robots in your own workspace, but to robots in other places. And so another company, we don't have access to this robot. I've actually never even seen this robot in person myself before. They sent some data to us, and we fine-tuned the model on that data and then sent them the model weights back. And they were able to run the same Pi0 model on their robot to do a fairly complicated task of making coffee, which requires taking the mug, putting it under the coffee machine, taking one of the cups, putting it in the machine, pressing a button, and so forth to eventually make coffee. So I think that this is kind of evidence of moving towards a paradigm in robotics where these foundation models can actually be deployed across a wide range of robot platforms in a wide range of locations. Now, how does this, kind of going back to the large language model pre-training and post-training regime, how does this compare? So the Pi0 post-training is analogous to the supervised fine-tuning phase of large language model post-training, but it's a little bit different, which is that so far we've looked at post-training on a single application or a single task. everything that I showed was without instruction following, but you could actually also add instruction following into the post-training phase. And in the paper, there's some experiments that specifically show that. And I also think that broadening it to kind of multitask supervised fine-tuning should also be quite feasible, just not something that we've done yet. And then one other natural question is, what about the reinforcement learning stage of post-training? I think that actually incorporating data from the model itself should lead to better performance, better speed, and better alignment, and so something that we're excited about doing in future work. Cool, so some takeaways. First, we found that independent development of post-training data in a pre-training model works well. You can actually see improvements independently from both of them and then combine them to get the best of both. Second, we found that training on all the data that you have for a complex task doesn't work, and trying to find a consistent strategy of high-quality data leads to better performance compared to just training on all the data. And as a kind of more of a research process, we found it very helpful to progress gradually, starting from a very simple folding task to the full laundry unloading and folding task. And this made it possible to make research progress in a steady way on a very complicated task. And then lastly, the post-train model, we find that it falls back on pre-trained behaviors if it encounters states that are not in the post-training data set. And then there's a lot more in the paper. I covered only a fraction of some of the experiments that were done. And I'd like to close by talking about a couple important future directions beyond kind of just the development and advancement of these kinds of models. The first is that I think that we still have a lot to learn about different policy design choices. And so some students and postdocs in my lab have been studying different choices with regard to history and action chunking on the modeling side. Second, I think that when we ultimately care about taking a model and aligning it with some objective, we've been looking at ways to do this more efficiently. So I think that oftentimes we just use fine-tuning for alignment, but if instead the model had a sense of different hypotheses for what the human might want, then we should be able to actually perform alignment much more quickly by selecting between those different hypotheses. And then lastly, at test time, we would like these models to be steerable so that, just like we can prompt a language model to do what we want it to do, ideally we can prompt other kinds of foundation models, including robotic foundation models, to follow different language instructions so that you can interact with them in real time. And I think that this will be really helpful for the deployment of these models. Cool. With that, I'd like to thank all of the collaborators on the Pi0 project, and happy to take some questions. Thanks. Over there? Yep.
So I have, well, very impressive work. Yeah, I have two questions. One is that for the fine-tuning, do you think that why stop at 1K? Can you, if you have 2,000 samples, would that be better? And the second question is that for the fine-tuning, for the folding the box, would that model still able to fold the cloth, or it's already lost the ability?
Yeah, that's a great question. So for the first question, why stop at 1,000? Getting high quality data of folding under a particular strategy and doing a very high quality fold, this is the more expensive data. Doing it efficiently and well and so forth. And so certainly we could try to collect more of it. It'll just take a little bit more time and potentially a little bit more expertise as well. Although we didn't do a specific ablation, and I do think that 1,000 is actually a pretty good amount and seemed to work pretty well for our use cases. And I should mention that teleoperating a robot to fold a shirt, it's actually a lot harder than you might expect. And then to your second question, we actually didn't experiment with whether it could also still do laundry. For the box construction, we only post-trained it on box construction, but I suspect that we could also post-train it on both box construction and laundry. And so, for example, in the mobile laundry task, we post-trained it both on unloading the laundry and on folding the laundry, and a single model was still able to do both tasks. So I think that it's possible to post-train on multiple tasks. If you only post-train on one task, then it might not work on the other tasks.
Thanks.
Over there?
Hello. I wanted to ask, how do you actually tell the robot what to do here? Is it just like a simple language prompt, or?
Yeah. So in all of the laundry experiments, we have basically a single prompt that's the name of the task. In this particular model, the name of the task was actually like batch folding singles. So it's, but I think that in these cases, it actually often ignores the prompt because if it sees a shirt in front of it, the data is always of folding that shirt. So it doesn't always listen to that. Now we have other tasks that where language is more important, and we prompt it with language as well for things like pick up the bowl or clean the table, those sorts of things.
Also, how do you like ensure that like the robot acts safely? Like for example, when the guy was like taking the shirt away and stuff, how would you like ensure that's like safe?
Yeah, so there's a few ways to ensure safety, like physical safety. The first is on the low-level controller, and the second is on the training. Maybe first on the training, we train it to do very particular things, and so the data, we'll train it to do the things in the data, and if you have safe things in the data, then generally the things that it will do are safe. Now this isn't a guarantee by any means, but if it isn't trained to like whack the person in the shoulder or something, then chances are it won't do that unless it needs to do that as part of the task, for example, if the person like directly gets in the way. The second is that there's ways to program controllers to have compliance, which means that if you push against the robot, it will there'll be some give to the robot controller. Also, these particular arms are not all that strong. For example, there are some washing machines that it's not strong enough to be able to open. And so that's also like you can put physical constraints on the strength of the robot and what it can do. So yeah, there's things on the controller side and so forth that you can do, but that will only go so far. Like for example, dropping glass on the floor is something that's maybe unsafe to do, but is not something you can control at the physical controller level.
Thank you.
Hi, so I have a question regarding to, as you mentioned, like a purely complex data may not really work well. So do you envision in the future, since even home robots, there are so many different types of tasks, is it like some sort of task we will need to pre-train a new, different foundation model, or it's like starting from pi zero, there can be a smarter way to really have a homework robot? Yeah.
Yeah, so I think that moving towards these kinds of applications, I definitely think that we can use pre-trained models, and we can start, for example, with the Pi Zero model or the next iteration of it in order to do them. And like what we found fairly consistently is that if you use these pre-trained models, not all these results are in the paper yet because some of them are more recent, but whenever we've approached a new task, and even with a robot that's not seen in the data, we've seen benefits from using the pre-trained model over just trying to train from scratch. So I think that that's very promising. And then I think that longer term into the future, I envision that we'll be able to simply prompt the robot to do the task that we want it to do without even having to do fine-tuning.
And next question is, how will you compare this Pi Zero method with, for example, OpenVLA?
Yeah, definitely. So they both use kind of pre-trained vision language models. And there's a few different kind of key technical differences. The first is that we use a lot more data to train Pi Zero, probably an order of magnitude more data to train it. And so as a result, it's a more general model, especially for more dexterous tasks, because there's a lot of dexterous manipulation data. The second is that OpenVLA uses discretized actions, while Pi Zero uses diffusion, and diffusion first is cheaper at test time, and also is sometimes is better able to model distributions. Although there's kind of I think lots of pros and cons between like discretized actions and diffusion. And then the third difference is the base vision language model is based on the prismatic for OpenVLA and is based on a newer polygemma model for Pi Zero. So definitely there's differences, like OpenVLA is also 7 billion parameters versus 3 billion parameters. Pi Zero I think would be stronger, especially for dexterous manipulation tasks and a lot of things in general just because it was trained on more data.
Thank you.
Yeah, I had a question, like, have you tested what happens in OOD situations where you put like a person on the table or the basket is not where it's supposed to be or all these kind of things?
Yeah, so in some of OOD situations, it'll do something quite reasonable. In others, it will not, I guess. It depends on how far it is from its data, its training data. One thing that was surprising to me is we have a very particular strategy of folding clothes, like kind of folding one part, then another part, and then folding like this way, for example, and then rotating and folding another way. And at one point we put different lighting conditions and we put some more kind of scenery in the background, in part because we actually just wanted to film the policy. And we found that it actually sometimes used a different folding strategy than I had ever seen before when it was in those kind of scenarios. So sometimes when it's in OOD scenarios, it'll just fall back on pre-training rather than on the post-training strategy. Other times, I moved one of the robot arms 5 inches to the left, and it actually still was able to fold a piece of shorts, which I was quite surprised by. I also tried putting a thick rug on the table, and in that scenario, it was able to fold, but because the friction of the table was very, very different from before, after it folded, it wasn't able to slide it to the corner. So definitely there's, it's able to have kind of some sort of OOD generalization, and then in other scenarios, it's a little bit too far from the training data.
Great, and then maybe a second question. Do you have any problems with like latencies if you're running these larger models?
Yeah, latency is definitely a challenge and not something that we actually, the particular approach that we use, we didn't end up managing to put into the paper, but the first thing that's very important to do is asynchronous inference. So because you compute 1 second of action, 1 second of actions, and then as you're executing those actions, you can then start to take the next image and compute the next one. Now, if you do that naively, it actually works very poorly because your predictions might not agree with what you started executing, and then you might actually end up in a state that's different from, and like think you're in a state that's different from where you are, and then actually get very jumpy behavior on the robot. And so we found it was very helpful to basically encourage the future predictions, the asynchronous predictions of the more recent stuff to be similar to the things that you're executing, at least for those time steps. Yeah, so that was very, very helpful. Some of the videos are still just fully synchronous inference, and we do find that fully synchronous inference for quasi-static tasks is kind of reasonable, although it looks a little bit more ugly and takes more time in the videos.
Okay, thanks.
Cool. We get in there.
Thanks a lot. Let's join me in thanking Chelsea again for the wonderful keynote speech. And it is my great pleasure to introduce our fourth keynote speaker, Professor Dawn Song. Dawn is a professor in the Department of Electrical Engineering and Computer Science at UC Berkeley. Her research interest lies in AI and deep learning, blockchain, Web3, security, and privacy. She is the recipient of various prestigious awards and several Test of Time and Best Paper awards from top conferences in computer security and deep learning. She is an ASM Fellow and an IEEE Fellow. She is ranked the most cited scholar in computer security, a minor award. She obtained her PhD degree from UC Berkeley and was a faculty at CMU. She is also named on the Female Founder 100 list. Let's welcome Dawn for the keynote speech.
Hi, everyone. Thanks a lot for being here. Yes, my name is Dawn Song. I'm a professor at UC Berkeley and also a director of a campus-wide center called the Berkeley Center for Responsible Decentralized Intelligence. So today I will talk about towards building safe and responsible AI and a path for science and evidence-based AI policy. So we are all really excited about the exponential growth in large language models, and they have made huge advancements on their performance and capabilities, and they are empowering new rich capabilities for a broad spectrum of different applications. While we are enjoying the exciting advancement of these AI technologies, on the other hand, it's also important for us to pay attention to the broad spectrum of potential AI risks. So in a recent report, our international scientific report on AI safety which I'm part of, we list out a broad spectrum of different categories of AI risks, including malicious use, malfunction, systemic risks, and so on. And also, I want to stress that as we deploy AI in the real world, it's also really important to consider the presence of attackers. For a number of reasons. One, history has shown that attackers always follow the footsteps of new technology development, or sometimes even leads it. And also, this time the stake is even higher with AI. As AI controls more and more systems, attackers will have higher and higher incentives to compromise them, and AI becomes more and more capable. The consequence of misuse by attackers will also become more and more severe. And hence, it's really important to consider building safe and responsible AI in the adversarial setting. Given the importance of this topic, there has been various policy efforts proposing to build trustworthy and responsible AI. When we look at safe and responsible AI, there are many different risks and challenges. Given the interest of time, I'll mainly focus on a number of them. So, in particular, in this talk, I will first talk about first main challenge: how we can ensure trustworthiness of AI and AI alignment. And then I'll talk about another main challenge, which is how can we mitigate misuse of AI. And then in the end, I will also share our recent proposal on a path for science and evidence-based AI policy. So first, let's look at the building trustworthy AI and AI alignment. There are many challenges in deploying AI in practice to ensure trustworthy AI and AI alignment. The list is very long, including robustness, privacy, hallucination, fairness, toxicity, and many others. And with the alignment goals, for example, we want to achieve helpfulness, harmlessness, and honesty. So again, given interest of time, I won't be able to cover everything. So in this part, I will mostly focus on robustness, and in particular, adversarial robustness. So I hope everyone here is already familiar with adversary examples. So these are essentially, for example, in this task for image classification, attackers can maliciously construct adversary perturbation when added to the image, even though the adversary perturbation is really small, that it's so that the end adversarial example image, you actually can't really see this perturbation. But however, the original image will make the image classifier give the correct classification, but the adversary example will cause the image will cause the classifier to give the wrong label. And so my group has been among the earliest to explore this type of phenomena, adversary examples in deep learning systems. So with my group and also other researchers working in the space, so what we have learned is that adversary examples is really prevalent in deep learning systems, and essentially all deep learning systems across all different types of domains, architectures, and for different types of tasks, they all suffer from this adversary example issues. And also this type of issue is not only this type of attack is not only effective under white box setting, where attackers actually know the details of the models, including architecture and weights, but it's also effective under black box setting, where attackers actually don't know the details of the model. And also our work, we were the first to show that the adversary examples also is effective in the physical world, that can even remain effective under different viewing distances, angles, and the conditions, and so on. And we also have the rare honor to have the artifacts of some of our earlier work now has become part of the permanent collection at the Science Museum of London. As a scientist, it's a rare honor to have our piece being part of the permanent collection at the museum. So now, fast forward, these adversarial attacks, as I mentioned, they are essentially prevalent or effective on all different types of deep learning systems. And as we talk about safety-aligned large language models, adversarial attacks, again, pose a serious issue for these safety-aligned large language models. So one of our recent work called Decoding Trust provides the first comprehensive evaluation framework on trustworthiness for large language models. With our work, we develop new algorithms and benchmarks that analyzes the behaviors of these, evaluates the behaviors of large language models under both benign and different types of adversarial environments. And we evaluate the behaviors of large language models under many different perspectives as listed here. The different perspectives related to trustworthiness of large language models. Our work has won the Outstanding Paper Award at NeurIPS last December, and also has won the Best Scientific Cybersecurity Paper Award given out by NSA each year for this year. So this is an example of our work showing that we actually, so with our evaluation framework, we automatically generate adversarial examples and demonstrating that large language models, again, they are vulnerable to these adversarial examples. And again, our work with this evaluation framework automatically evaluates the trustworthiness of large language models across many different perspectives. And our work showed that these large language models, in general, they can be very easily attacked and have many different types of risks. And also, with the others' work, they also, other researchers have also shown that these adversarial attacks, they can also be transferable to attack black box large language models. And also others have shown that with the multi-model, actually in the multi-model setting, adversarial attacks can be even easier to do, and you can similarly break safety alignments as well. So far I've talked about adversarial examples at inference time, where attackers essentially maliciously manipulate the inputs. Essentially, you can view it as prompt engineering or jailbreak to actually cause the large language models, in this case, to misbehave. For example, essentially break the safety alignment. And adversarial attacks can also happen at the training time, including both pre-training and fine-tuning stage. And in this case, we call it the data poisoning attacks. So again, my group was actually among the first to investigate the data poisoning attack as well. And we developed, in particular, what we call targeted backdoor attacks. In this particular case, this is a facial recognition system, where we showed that attackers by just poisoning a very small fraction of the training data sets, and also in a very stealthy way, that with the visual inspection of the training data, you actually can't really see these injected backdoors. But however, under this attack scenario, they learned facial recognition system. Under normal situation, it will perform correctly. But however, when a user is wearing a special type of glasses, then the facial recognition system will be essentially fooled to misrecognize this person as a particular targeted person. And recently, other researchers, including, for example, a researcher from Robotic, has also shown that using this type of data poisoning attack, attackers can also inject backdoor into the safety-aligned LMs. So in this case, during the fine-tuning stage, they can inject backdoor such that when certain phrases appear in the prompt, the attacker, so the system, the LM will then generate vulnerable code instead of just normal code. So, So the interesting finding is that even after actually safety training, this type of attack still can persist. So that during normal situation, again, the model will give out a normal, like a output normal, like a generated code. But however, when the spectral phrase appears, the model will actually generate vulnerable code. And also, during fine-tuning, then attackers can also inject poisoned data points, and in this case, causing adversary fine-tuning. And other research work have shown that this type of adversarial fine-tuning attackers with very small number of adversarial poisoned training examples with very low budget can very easily essentially break the safety alignment mechanisms, so that the end result fine-tuned model will actually not have the safety, will no longer have effective safety alignment. And actually, our work actually was presented here at NeurIPS, demonstrated another type of data poisoning attacks. In this case, actually, we can insert backdoor into RAG in the agent setting in our work called agent poison. So all this work have shown that these deep learning models, including the large language models, are vulnerable to adversarial attacks. And in fact, with our work, so when we started working in the field, it was very early. There were actually very few papers a year in this field. And since then, the field has grown tremendously. It has grown exponentially. Every year, there are now thousands of papers in this domain. But however, I would say, unfortunately, most of this progress has mainly been on the attack side. And the community has been very creative in coming up different new attack methods. However, on the defense side, the progress has been extremely slow. The community almost has made, I would say, like very, very little, almost no progress on the defense side. So today, we still don't have effective general adversarial defenses. However, AI safety mechanisms need to be resilient against adversarial attacks. As I mentioned, current AI alignment mechanisms are easily evaded by adversarial attacks, and effective AI safety mechanisms need to be resilient against adversarial attacks. And hence, adversarial robustness is a huge open challenge for achieving AI safety. So the question is then, what can we do? How can we address this huge open challenge? Here, I'll give a couple examples of our own recent work as promising future directions. The first one I'll talk about is on representation engineering. So this is a top-down approach to interpretability. So in this work, together with other collaborators and my former students and so on, we essentially try to build models to monitor the activations of the neural networks during inference time. So in particular, we design contrastive stimulus for different types of tasks. For example, here you can see, pretend you are a dishonest person or you are an honest person, and you can tell me about a certain topic and so on. So then we monitor the activations of the neural networks during inference time and build models to essentially try to build models to predict the essentially the behaviors of these models. So what our work has shown is that using this approach, we can actually identify, for example, certain directions in the representation space, in the activation space, at different layers that actually correlates with different types of behaviors of the model, such as whether the model is honest, or dishonest, or whether it's hallucinating, and so on. And furthermore, another really important aspect of this work is that instead of just being able to, we call representation reading, being able to monitor the model behavior from reading the activations, we can also, using the learning model, to modify the activation of the actually modify the activations of the model during inference time, and this is what we call representation control. And using this method, we show that actually, for example, we can amplify the activation along certain directions, using other approaches, we show that actually we can, for example, make the model more honest or dishonest. And another work that we did recently, also utilizing this approach, is in the domain of controlling political leaning of large language models. So in our recent work at EMR NLP, we studied the political leaning of large language models and showed that these large language models, they in general have left leaning. And for example, they would they choose over Biden over Trump before this was done before Biden dropped out of the election. So the question is, how can we actually mitigate political leaning? So in this case, we actually use the representation control method. Our preliminary work showed that we can identify, again, these directions correlating to the political leaning of the large language models. And as we modify the activations, we can, for example, in this case, make the model more neutral. So from the examples here, you can actually see the output from the model with or without this representation control methods. And you can see that the representation control methods can really make the model output actually much more neutral. And for, so this is actually entirely another very big topic, is how LM can, the impact of LM on future of democracy. And you can go to their website to learn more of our work as well. So this is one method. And another direction that's very important is how we can actually give better guarantees on AI safety. So together with other leading AI researchers, we recently launched an initiative on quantitative AI safety initiative. And the goal is how we can actually provide better guarantees on AI safety. So of course, this is a really challenging topic. So towards this goal, so in particular, my group and together with other researchers, collaborators, in particular, we're exploring a particular direction that with a more constrained scope is building secure by design, safe by design systems with essentially provable guarantees. And this is also motivated by my personal experience and also the community's experience in cybersecurity over the last few decades. In the last few decades, essentially the security paradigm has had, the security field has had several paradigm shifts in terms of how we develop effective defenses. The first type of defense is what we call reactive defense, where we develop methods to detect, for example, malware, and then, for example, to block them and so on. But this approach is not very, has a lot of limitations and challenges, given that it's a cat and mouse game, and the defender may not be able to detect the attacks fast enough. And the second paradigm then is on defense is proactive defense through bug finding, with the goal that defenders can do this automated bug finding through fuzzing, symbolic execution, and so on, to find vulnerabilities and patch them before attackers can find them. However, this also has a challenge that defenders may not be able to find all the bugs, and attackers only need to find one vulnerability and successfully exploit it to actually be able to succeed in its attack. And this motivated the new paradigm, which is proactive defense through secure by construction. So with this approach, essentially, we try to architect and build provably secure programs and systems with actually provable guarantees. So in this case, the developers can specify desired security properties, and then to prove, and then provide formal verification that the security property is satisfied. And this formal verification can be done at different levels, including the design level, for the product level, or the implementation level. And also, through the hard work of researchers in formal verification, we actually have entered the era of what I call formally verified systems, where we actually have many different systems that have been formally verified, including SEL4, like microkernel, compilers, file systems, and so on. However, a huge challenge of this is that it's actually very labor-intensive to do formal verification for these systems. And for example, SEL4 has taken tens of proof engineer years. So motivated by the importance of this approach, even early on, like 5-6 years back, so my group, again with other collaborators, including, for example, the paper co-author with Ilya from OpenAI and others, we were among the first to explore using theorem proving, using deep learning for theorem proving. So our work back then showed that we can use deep learning to help automate certain steps in theorem proving. But however, back then still we had the compute was much less, and the techniques were not as advanced. Now, fast forward, with the recent advancements in large language models, with much larger compute and so on, I feel that we are hitting an inflection point for actually using deep learning for theorem proving. And so we recently actually have a paper that will be released soon, and that actually lays out the future directions and roadmaps in the space. The paper is called Formal Mathematical Reasoning, A New Frontier in AI, with a number of other collaborators. And you can see the current drafts at this URL, and we would love to get your feedback. So, so the hope is that we can really leverage the advancements of large language models and, in general, the recent AI advancements to actually really help us to make significant advancements in automating theorem proving and for formal verification. So, in particular, currently, most of the advancements on AI for math is more on what we call AI for informal math. This approach has yielded a lot of great progress, but however, there are a number of limitations, including data scarcity and the lack of verifiability. And our view is that in order to make to really address the challenges that the problems that we want to address, we actually need to advance AI for formal math, for theorem proving, through including both auto-formalization, translating informal math to formal math, and also to automate the theorem proving. And with this paper, we lay out the future directions and roadmap to bring the community together to make progress in this domain. We hope that with this type of technical advancement, instead of just training agents to play games like Go, we can actually then train agents to do automatic theorem proving for program verification. And this, in combination with program synthesis, this can then enable us to automatically generate provably secure code. So with this approach, we hope that we can truly utilize AI to build provably secure systems with safety and security guarantees. With this approach, we can do code generation and proof generation together. And this approach can help us to reduce the arms race and build provably secure systems resilient against certain classes of attacks. With this approach, of course, there are many open challenges. So this type of formal verification approach, it applies to traditional symbolic programs. But however, it's actually difficult to apply to non-symbolic programs such as deep neural networks. For example, in this setting, we don't even have precisely specified properties and goals. So for example, we want to ensure that autonomous vehicles do not drive over pedestrians, but however, we don't even have precisely specified definition for what a pedestrian is. So, and also future systems will be hybrid, combining symbolic and non-symbolic components. And hence, the current formal verification and secure by construction approaches has limited applicability. So we hope that as we make progress in this domain, we can also explore new approaches to further extend this to even these hybrid systems. Okay, so that's the first part on ensuring trustworthiness of AI and AI alignment. So I will also briefly talk about the second challenge on mitigating misuse of AI. AI is a dual-use technology. It can unfortunately be misused by attackers in many different ways. So in particular, in this case, I will focus on the domain of cybersecurity. In particular, one of our recent work focuses on how we can explore and analyze the impact of frontier AI on the landscape of cybersecurity. So when we compare this, so in traditional security, we have attackers and defenders, and we have traditional software system, which are symbolic programs written by humans. But however, with the frontier AI, now attackers will be assisted with frontier AI, and defenders will be assisted also with frontier AI. And also the software system, as I mentioned, is now hybrid, including both symbolic programs that are written by humans and AI, and also non-symbolic programs and AI, such as AI models. So the question is, in this case, who will win? Will attacker or defender win with the frontier AI? So that's a part of also our recent work on doing this analysis, how frontier AI will impact cybersecurity. And in order to answer this question, there are many different aspects that we need to actually go through. There's a process. We need to know the enemy. We need to understand, analyze the impact of misuse AI in attacks. And also we need to know the defense and the impact of AI in defenses. And we need to understand the unique asymmetry between defenses and offense. So first, when we look at how AI can be misused for attacks, then there are two different aspects: how AI can can assist attackers to attack machines, and how it can assist attackers to attack humans. So again, my group was actually, we wrote the first paper on using deep learning for program binary analysis, and also some of our earlier work, we were the first to show that actually using, for example, graph neural networks, we can actually essentially use deep learning to do effective vulnerability detection for known vulnerabilities in binary code, and for example in IoT devices and so on. That actually the technology is much more effective than traditional program analysis techniques. And also more recently, researchers have shown that our agents can autonomously hack websites with the simple for simple types of vulnerabilities, and can autonomously exploit one-day vulnerabilities and so on. And these are just a few examples, but really in order to understand this issue, how AI may impact on the attack side, we actually need to perform systematic analysis across the different stages of cyber attacks. And this is some early results from our analysis showing that how AI's capabilities and impacts and its impact levels in different attack stages. And besides attacking machines, AI can be used to attack humans, and actually humans are the weakest link oftentimes in attack, weak links in secure systems. And in fact, many CISOs and security practitioners, they recognize that the most common cyber threats facing business and individuals today is phishing. And today we are already seeing Gen AI causing huge increase in social engineering attacks. And also, unfortunately, today we see AI capabilities really have been used to attack humans, actually in large scale in the real world. And again, so that's for how AI can help attackers. We also need to understand how AI can help defenders. So I mentioned earlier, right, there are these different defense paradigm in the security domain. So we can quickly look at these. So first of all, reactive defense. Unfortunately, in this case, I would say that AI actually will help attackers more than defenders in reactive defense for a number of reasons. Given interest of time, I won't be able to go through it. And also similarly, AI can enhance defenses for bug finding as well, such as what's been demonstrated recently with the Google Project Zero. But however, I would say that in this case, still, even for bug finding, this type of defense, AI will actually help attackers more because of the unique asymmetry between defense and offense. For defense side, defender needs to be able to essentially find all bugs and fix all of them to prevent and need to prevent all attacks in order to succeed. But attackers only need to find one successful attack, one vulnerability, and a successful exploit for the attack to succeed. And also the cost for defense can be much higher than attacks, and deploying defense, even when it works, can take a very long time. When the defender needs to develop the fix, need to do a lot of testing, and need to do deployment globally. And today, a lot of legacy systems actually are still not patched. And also AI attackers can learn about vulnerabilities and generate exploits using public information of the patches and can exploit systems before they can be patched. And hence, AI can help attackers more than defenders in bug finding as a defense. And hence, this motivated the paradigm of proactive defense with the secure by construction. As I mentioned earlier, essentially by using the approach of architecting and building properly secure systems, using automated program verification and code synthesis together, using AI, we hope that we can actually develop the ultimate defense using AI against attackers. And on the helping user side, I do strongly believe that AI essentially can provide the only defense against social engineering and phishing attacks. And so several years back, we had a project on using deep learning to actually build chatbots to help protect users by monitoring the communication between users with the outside world to try to detect social engineering attacks and to try to defend it. For example, it can actually try to engage in conversations with attackers and try to then actually waste attackers' time and resources. Now, fast forward, back then the technology itself didn't work very well, but now fast forward with LLM and so on, I think this is a really exciting area and direction to develop better chatbot and personal assistants to help protect individuals from social engineering attacks and phishing attacks. So again, given interest of time, I won't have time to go into the details. So one challenge is, as I mentioned, there's a huge asymmetry between attacks and defense, which makes it easier for attackers to actually utilize AI technologies earlier and at a large scale to help on the attack side, whereas it's harder for defenders to actually, for a number of reasons, to actually be able to benefit in the early stage. And the consequence of misuse AI in attacks is vast, and misuse AI can really help significantly reduce the cost for attacks and to help increase the scale for attacks. And today, already, there's reports, for example, from AWS, the head of security, that they used to see 100 million attacks per day. Now it has gone up to 750 million a day, just over the last 6 to 7 months. So the lesson that we're learning here is that AI is already helping attackers, and as the cost of attacks going down, we expect to see unprecedented increase in attacks. However, the world was not prepared for pandemics such as COVID, despite early warning, and this time attacks assisted with AI can be much worse. So here's some lessons we learned also early on from some of our earlier work in the domain of medical device security. So my group with other researchers, we were the first to do actually medical device security analysis in the public literature. And our work at the time showed that we were able to identify critical vulnerabilities in these medical devices. However, at the time, FDA's approval process actually for medical device did not even include the mention of security. And only 5 years later, given our earlier work and also others' follow-up work, FDA issued guidance recommendation on medical device security in their guidance. And so the lessons learned here is that security space is very complex, and frontier AI will have huge impact in cybersecurity. And in the near term, AI will help attackers more than defenders. So it's important for us to learn from past lessons and act now. We need to build and deploy plans to improve security posture to get ready, and we need to build AI solutions and digital assistance to protect humans against these bot attackers. And we need to use AI to build secure systems with provable guarantees. And so in our paper, we also have a call to action to have the community come together to improve and leverage frontier AI to strengthen cybersecurity. So far I've talked about the first two challenges, how we can ensure trustworthiness of AI and AI alignment, how we can mitigate misuse of AI. So now I just want to conclude with our recent proposal for a path for science and evidence-based AI policy. So overall, our goal, I think for the whole community, is that we want to advance safe AI innovation to ensure its potential benefits are responsibly realized and widely shared. So in order to achieve this, we actually need a social technical approach. And given the importance of AI safety and just in general the impacts of AI on society, this year we have seen a sudden proliferation of AI bills. So for example, currently there are about 120 AI bills in progress at the federal level, and at least 45 states have introduced AI bills, about 600 bills. However, at the same time, we are seeing huge fragmentation in the AI community on approaches to AI policy. AI research and policy community lacks consensus on the evidence base relevant for effective policy making, including what risks should be prioritized, if or when they will materialize, and who should be responsible for addressing these risks. This has also been seen from the heated debates on the recent SB 1047, the California bill. So building a safe AI future needs a sustained social technical approach. Technical solution alone is necessary but insufficient. However, ad hoc regulation can lead to a number of issues, including suboptimal solutions, potentially negative consequences, and more importantly, can lead to lost opportunity to avert disastrous outcomes and fragment the community. So what is a better path to a safe AI future? Here, this is our recent proposal in order to address many of these issues. Here's our recent proposal on the path for science and evidence-based AI policy, together with a number of leading AI researchers, and also in policy as well. And for more information, you can go to this website, understandingaisafety.org. So with this proposal, we emphasize that AI policy should be informed by scientific understanding of AI risks and how to successfully mitigate them. However, current scientific understanding is very limited, and hence the proposal proposes that AI policy should be science and evidence-based, and we should prioritize advancing scientific understanding of AI risks and how to successfully identify and mitigate them. And in order to achieve these goals, in the proposal, we also propose 5 key priorities to advance scientific understanding and science and evidence-based AI policy, including research marginal risks, increase public transparency, monitor pre-deployment risks and post-deployment harms, strengthen societal resilience, and bridge fragmented communities. Again, for more information, you can go to this website. So given the issues of time, I won't be able to actually go into the details of this proposal. And again, so for this proposal, we actually propose a combination of science and policy based priorities that we need to better understand AI risks. Both it needs to be comprehensive. We need to have a comprehensive understanding of a broad spectrum of AI risks, and we need to analyze it with the marginal risk framework. And we need to increase transparency on AI design and development. And we need to do both in-lab testing and develop better science of evaluation for identifying AI risks early on, and also do active monitoring and adverse event reporting for post-monitoring and reporting of AI and post-deployment AI harms. We also need to develop mitigation and defense mechanisms for identifying the risks, to develop both new approaches for safe AI beyond the current alignment mechanisms, as I mentioned earlier, and also to develop resilience and immune capabilities in society to improve the societal resilience to attacks. And finally, we need to build trust and reduce fragmentation in AI community. And in the end of the proposal, we also propose a call to action to bring the community together to build a forward-looking design and the blueprint of future AI policy, where we map, we have this what we call if-then protocol, or conditional response, where we map different conditions that may arise in society to candidate policy responses. And so far, we have gotten really positive feedback from the community. There are already volunteer contributors from about 200 different institutions have volunteered to contribute. And as the next step plans, we plan to organize multi-stakeholder meetings to bring the community together to make progress on the different priorities that we propose in the proposal. And again, if you are interested in contributing and also to learn more about this, please go to understandingaisafety.org. And also, again, if you are interested in the AI for formal math and for program verification, you can go to this link to see our paper, and we'd love to get your feedback. And finally, I also wanted to briefly mention that this semester I have been teaching a MOOC, a massive open online course on large language model agents. We have about 14,000 enrolled online. And also we have a hackathon, which actually is due later this week, where we have about 2,500 developers that have signed up. And we actually have a safety track also. And also, given the success and the huge interest in our agent MOOC, we'll also have a follow-on version of the agent MOOC on advanced LM agents in the spring. And in particular, we'll focus on more advanced topics such as reasoning, planning, code agents, web agents, and also AI for math and theorem proving. And again, you can learn more at agents-learning.org. With that, thank you very much.
Thanks a lot, Dawn, for the great talk. Now we will open up the floor for the QA session.
Hi, Professor Song. Thank you so much for your enlightening talk. I have a question about defining AI safety, and I'll give you some context for the question. When we talk about the FDA, globally or universally, we have this goal of avoiding death or avoiding suffering of people. And when we think about regulating safety for autonomous vehicles, there's this idea of avoiding accidents or avoiding collisions. When we think about security, you're avoiding the system from working in a way that was not intended. However, in today's discussion, from the earlier keynotes and even in your talk, when you listed the different dimensions or areas of safety, I realized that we are dealing with an issue of morality here, and people view the world differently, right? There are some people who think models should be historically accurate. There are others who think that there should be a fair balance of different demographics. And because different people have fundamentally different beliefs, it's a little hard for me to conceptualize when we say safety, what exactly we mean. So my question then becomes, when we say AI safety, what do we mean? Like, if we have a regulating body that is trying to ensure safety of AI, what does that look like?
Okay, great. Thank you. That's a very good question. So overall, AI safety is an extremely broad topic. Essentially, again, as I mentioned earlier, so the goal for AI safety is that we want to foster innovation while at the same time, essentially to ensure that AI does not cause harm in society. So essentially, AI safety is about how we ensure that AI will not cause harm in many different, like a very broad spectrum. So for example, here as it's not shown here anymore. So as I listed earlier in my talk, so also as I mentioned, given the interest of time, so the talk cannot actually cover all different types of risks of AI, and hence we can only cover a small number of them. But actually, you can also go to our reports, this international scientific report on safety of advanced AI. So really, that's also part of the proposal that I mentioned earlier, is that we really need to have comprehensive understanding of AI risks. This actually includes all these different types, including malicious use that I mentioned, and the malfunction, and the systemic risk. And in systemic risk, actually can be even broader, even include, for example, climate environment issues, labor markets, even broader. So I would say, yes, AI safety is very broad, and we do need to have a comprehensive understanding of AI risks in this broad setting.
Next question. Yeah, okay. This question is more specific for the LLM safety that you started with. So when we think of LLMs, there's kind of two ways of making them do things they're not supposed to. And one of them is kind of this prompt engineering, red teaming. And the other one is kind of what you presented, this, adversarial attacks, which kind of comes from a different direction a little bit. And I wonder if how do you see those two being connected? And do you think they're connected? Do you think they're basically the same problem? Or do you think they're different problems?
Okay, so just to clarify your question, so here you are talking about for example, to ensure certain safety alignment and so on.
Yes.
You want to say what are different ways to evaluate it?
Well, I'm saying there's kind of two different ways. One is you can try to do an adversarial attack where you trick it. The other one is you can say my grandma is dying and she needs to know.
I see. Okay. So so these are essentially different ways you can create the attacks. But when you say adversarial attacks, there are different. How should I put it? The term also can be interpreted.
There's a lot of different ways you can.
Different ways to interpret the terms, but essentially these are all the same type of approaches that you are trying to generate. Essentially, different types of inputs that actually has been maliciously generated, but there are different ways. So typically when we talk about these adversary examples that I showed earlier, oftentimes you, for example, use optimization methods to generate these adversary examples. But in other ways, maybe humans, like this grandma type of thing, the humans are doing the optimization. Humans are actually creating this type of malicious inputs or scenarios that actually fool or mislead the LLM. So essentially, these are different methods to try to achieve the same goal.
Do you think the defense, I guess, is this? Do you think it's like the same problem underneath, or do you think it's like completely two different issues?
I see. I mean, in terms of the actual reasons why, in this case, under these different types of attacks, how it actually gets broken, the safety alignment gets broken, there may be different underlying reasons. So, for example, when you have this grammar thing, then maybe it's following this instruction that actually, it's following this instruction, but actually then in the process, it broke the safety alignment mechanism. And in the other, for example, using adversarial, these adversarial examples using optimization, maybe then internally somehow tricks the LM to then get into some weird state and then behaved wrong and then broke the safety alignment mechanisms. But these, I think, also in some sense they are also related. So the important part is that how do we actually develop better defense mechanism against all these different types of attacks. And also these, in the end, you can do mix and match and so on. So, I think there is a very fluid landscape of attacks, and then oftentimes we need to, and as I mentioned, so for our defense side, we have